Great. So I think now the attendees number is stable, so we can start. Thanks a lot again for joining us today. Before we start the webinar, I just wanted to let you know about our YouTube channel. So probably you already know about the YouTube channel. So you can subscribe that you don't miss any video from European Society of Biomechanics. And I just wanted to announce that we created two playlist journal club. So one journal club as a pitch. So it's about introducing the paper. So the author will introduce the papers in a brief video, and we upload them actually before the journal club session, and then we will also upload the journal club session in a separate playlist as the journal club sessions. So you can check the papers. You don't hesitate to contact us if you want to present your paper to the European Society of Biomechanics. Our colleague in student committee, Ingmar, is responsible for journal club, so you can contact us, and we will be happy to have you in one of our journal club sessions. So today's webinar is about OpenFoam software. Dr. Sangita Swapnasrita will present this software to us. And so she is currently a postdoctoral researcher at MERLN Institute at University of Maastricht. So she is going to introduce us how we can start working with this software and give us a brief insight about the software. Probably we will get to know how we can use this to solve our computational challenges in biomechanics world. So the presentation will be 45 minutes, and then it will be followed with 15 minutes Q&A session. So we will encourage you to write down your questions in the questions box in the right side of your screen. Probably you see that. And we will write down all the questions, and we try to answer all of your questions afterward. Thanks a lot. I give you now the mic and screen, of course, to Sangita. Great. So you can start, Sangita.
Okay. Thank you so much for the introduction, and also thank you for giving me the opportunity to share my experience with OpenFoam. So hello everyone, welcome to the ESB webinar for OpenFoam, where I'll provide a small insight into how OpenFoam can be useful for your biomechanical applications. I'm a postdoctoral researcher here at MERLN in Maastricht University, and I do computational modeling and I have always done computational modeling. So to introduce myself, it's not working again. Okay, so for my master's, I did a simulation to find viscosity of lower alkanes and water using Monte Carlo and molecular dynamics. For my PhD at University of Bremen, I worked on a reaction model that was developed in OpenFoam, and my task was to improve the efficiency of the model, so to reduce the computational time required to use it. In my PhD, then the second project of my PhD, we collaborated with University of Chalmers, and they had a microchip reactor. So I validated that using the improved reaction model. For my postdoc, I started here in 2021, where I first did transport kinetics in COMSOL, and right now I'm trying to model dialysis in Python. So all my projects have always been using computational modeling, and I really like it as a medium of doing projects. but OpenFoam was the one that I worked with longest, and I have a small soft spot for it. So during today, we will go through a brief history of OpenFoam, how and where you can use OpenFoam. We will set up a small test case so that we can see how it, if it is something feasible for you. We'll run the test case and we'll visualize the data and helpful tricks. Before I forget, the presentation and the test case will all be available. I'm not sure about the presentation, but the test case will definitely be available on GitHub. So you can always look back and use the same test case as I did here. Okay, so what is OpenFoam? First of all, it is open source and it's a mathematical calculator. So it is used for field operation and manipulation like we would have for any kind of flow field. So it was a product designed from OpenCFD by Henry, Chris, and Matthias in 2004. It uses a vast C++ library, and now it is available on Windows, Macs, and Linux. And 2 versions are released every year in June and December. So it is very up to date in that sense. There are many benefits, but the biggest benefits of OpenFoam are the huge source guide. So everything is open and everything you can customize to your own needs. There is a repository of all the C files. So back, like dating back to their first version, so you can see how they have changed. And if you need some particular source file, you can always look it up and you will find the C file that you need in GitHub. There are now thousands or more than thousands of tutorials from OpenFoam themselves and also by a lot of people on YouTube. You can find these tutorials, and the most valuable part of this OpenFoam open source software is the forum. So there is a CFD forum for OpenFoam, and it is very active, and people who are specialized in debugging OpenFoam codes are there, and they reply within 1 or 2 days, and you can often find solution to your problems there also. So to write it more scientifically, it is a C++ based simulation software, and it's often used for engineering and scientific context. I've seen it being used for mechanical applications, even though I have not used it yet, but it is used maybe for fluid flow around a scaffold, or like here in the right, for a hip joint movement and how the stress is at each point. You can also do that. So coming back to the structure of OpenFoam, we have 3 different important parts. So the first and the most important is the core OpenFoam libraries in C++. Then we have a whole list of solvers and utilities. So these are like your apps in your phone. So you use the app, but basically the behind the code is written in the source. And then we have finally your run or your executable files. So let's say you have a file on a particular app, so that will be your run folder. And this is me showing my OpenFoam using GitHub. So after you install, there will be a folder like this with only the run folder inside it. I will repeat that again. So when you install OpenFoam, there is a very nice installation guide, and if you follow that through completely, you will reach already at this point where you have your folder run there. So to set up, first let's take a small test case where we will analyze flow field around a porous scaffold. So scaffolding is a very common theme for biomechanical applications. So I thought let's use a very simple one. And this also incorporates a lot of different things which I want to show, like the different utilities that we can use in OpenFoam. So I thought this was a nice case. So first and foremost, we have a domain. So this can be any kind of box or sphere in which you want to see what is happening. So here I have chosen a simple cubic box as my domain, and then this is my scaffold. This is also quite simple. So I have a porous cube, and then on top I have these cylinders which are not porous, and I want to see how the flow field will develop around this scaffold. So if I open my run folder, in which I will have my user case, I have my test folder, and then I can see 3 folders inside it, which we will go through now. So this is the prepping part of the OpenFoam simulation. So you have to prepare the mesh, you have to prepare the initial boundary conditions. So this is what is the preparation, and this is called as utilities. So we have pre-processing utilities, so to create the domain and how you will break down the domain. Then we have also parallel processing, so you can distribute your work between the different processes in your computer to make your work faster. Another one is to manipulate the mesh. So let's say you have a very tiny corner, or you have a lot of holes in your scaffold, or you have a lot of fibers. So you can manipulate your mesh exactly according to how your fibers are from a CT scan, from AutoCAD. So you can use that utility also. And then you also have visualization and calculator also included in OpenFoam. So it is kind of a whole package where you can go from point 0 to your endpoint without leaving the software. And the OpenFoam guide itself has a very nice description of each of the utility that is available under each of these branches. So first, I will describe what I'm doing for my pre-processing. So I will take my domain and I will specify the vertices. It is needed that you specify your vertices in a particular order. This is also there on the OpenFoam guide. Plus, there is a nice playlist that I have attached here where they walk through each part of the OpenFoam of this particular block mesh. So you're trying to convert your domain from a big cube into smaller so that you can use finite volume method afterwards. Then we specify how we will connect all these vertices and what will be our mesh size. So you might want to divide it into very tiny blocks and then integrate to get your result, or you can keep it very coarse and see your results at the end. Then also we have to define like how the edges are. They can be straight, they can be arc, spline. You can pick whatever way you want. And then finally is specify the boundary patches. So what is happening at each face of my cube? Is it an inlet? Is it an outlet? Am I having a periodic boundary condition? And then you finally get something like this. So and how do I do this? So if I look at my OpenFoam, I can see that this is my block mesh dictionary. And then I have my vertices where it is V0, V1, V2, then the blocks, and blocks will say how it is connected. And then I have all my edges, and all this is also commented in the block mesh dictionary. So you can see, I'll just play it once again and I can pause through. So, oh, sorry. Okay, so like I said, so everything has to be written in a particular order. So here I have defined my cube by stating like the X, Y, and Z coordinates. Then I say using these vertices, so this is my 0th vertex, this is my first vertex, second vertex, and how I will connect them. So I have here used a hexahedral mesh. So I use a hex and then I specify the 8 vertices. Then I specify how many cubes I want in each direction. And if you want to use adaptive mesh, you can here also grade your mesh differently in different directions. If I play it a bit forward. Okay. Okay, so then I say how to connect each of the vertex, and then finally the most important is I define how each of the boundary is, which is here. So I say like which one is my outlet. So using 4 vertex, I show which one is my inlet, which one is my outlet, which one is my front, back, top, bottom. It doesn't necessarily have to be that name. You can have, of course, any sort of name, but this is the part that is important, which is like, does it let everything in? Is it a wall? Is there slip condition? Is it a periodic boundary? Am I seeing symmetry here? So you can do a plethora of different types of boundaries, like you can do with any model, but you have to write it in a specific way here. There is also opportunity to do 2D cases, although this is mostly for 3D. People also use for 2D. That's why they have done this, where you can define all your 6 faces in a hexahedral, but then you can merge 2 of them so that you can also perform 2D simulations. Okay. So going to the next step. So we defined our domain. Now what we want, so we defined the domain. Now what we want to do is make the inside non-porous structure that I showed in our test case. So to do that, first we have to take our whole domain and define a set of cells inside that I want to define as something else. And then I want to convert that into a zone. So it's basically like keeping a thing constant inside your domain without even if you change something around it, that part itself will remain constant. This can also be done for not only for cells, it can also be done for edges. So let's say you have a heat source on one face, then you can change this set of faces into a zone, and that you can define that as your heat source. So then you can also solve things for these faces, but it will always retain the property whatever you have given to it. So basically here I'm trying to say that let's take this particular box and I want to make it porous. So I will first convert the particular box. So I take here a source. So this defines the endpoints or like the diagonal opposites of my cube. And then I convert it into a cell set and I name it something. Then this becomes important. Then I use that to convert it into a zone. So why didn't we stick to cell set? It has something to do with dynamic mesh, and I will not go into that today. Then once I've defined my zone, I can define, so I took the name that I gave there and I changed the porosity. So it's a very common type of porosity expression. So it's called Darcy-Forchheimer, and then I use I use that to define my porosity in different direction. So here I have my D in all 3 axes are same because I wanted to keep it very simple. Okay. So now I got my porous cube and I want those tiny little non-porous cylinders on top of it. So that will require me refining the starting mesh. So this is probably for me the highlight part of OpenFoam. I have another favorite, but this one is also very nice because here you can take whatever scaffold you have by yourself, because we always take images of these scaffolds, and then you can convert that using OpenFoam itself. There are many different utilities to convert like a VTK foam to OpenFoam foam, or you can also there is also from Fluent to OpenFoam. There is ANSYS to OpenFoam. So people have designed many different tools in OpenFoam so that you can convert your own mesh to a OpenFoam style mesh without you having to do anything extra. So for me, I use Snappy Hex Mesh to make those tiny cylinders on top of it. So I have my box with the porous structure, and then I want it to look something like this, like the middle one. So I will use Snappy Hex Mesh to do this. So just to give you a resource here. Andrew Jackson, so the last one, he has some very nice slides on this particular snappy hex mesh. Snappy hex mesh is huge because it is very, very refining. So it asks you a lot of things. I will not go into all of that, but yeah, you can follow his slides to understand like what each part means. So if I go here, so this is my snappy hex mesh. So in this, what I'm doing, basically the most important part is here in the geometry. So I'm adding those cylinders. So if we go down, oh, sorry. So here I added my 6 cylinders on each of the 6 faces, and I define them as support because they are one kind of support. And then here I define how the cylinder is to be made, where it is to be placed, and all that. And then there is like you can see, I define all the 6 cylinders separately, but I give them the same name. So they will all be compiled as one area. And then you can see like there is a huge list of commands that follow, and everything has been explained nicely. So you can always look it up and also follow his slides for that. So then what kind of solver will I use? There are many different types of solver also available. There are different categories of solvers that are available for CFD. So for example, we have basic to solve simple thermal, diffusion, and transport. We have also heat transfer type of solvers. We have for incompressible Newtonian and not Newtonian fluids, we have different kind of solvers. We have discrete solvers like the one that I used, DSMC foam, in my PhD was a discrete solver. Then we have multi-phase, so to use for your biphasic fluids. And then we have for stress analysis. So for a description of all the solvers, of course, you have the guide. And then this is a resource where they help you decide, like he explains how you decide a solver, like depending on what conditions you have, what you're trying to simulate. You can use this as a guide to decide what solver you should use. So there are, like I said, many different solvers available inside, which like highlight like what exactly you want to do. It like drills down on it. So you can see icofoam, Laplacian foam, and multiple different. So in the next slide, we will I will show you like what other foams are available. So this is like the source folder, and in this, if I go to applications and then solvers, you can see all the different types available. And in incompressible, I open icofoam, and you can see the description, and you can go through the file to get a feel of like what it does. And you can pick out like where which kind of equations are used. It's written in C++, so might be a bit difficult to understand directly, but nevertheless, there are also explanations, like I said, in the OpenFoam guide. For our test case here, I use SimpleFoam, which is a steady state solver. It's usually used for turbulent flow, but we will use it for a laminar flow, and it uses the simple algorithm. So this algorithm is very simple. I think that's why they gave the name simple. So it solves sequentially for different variables. So kind of like, I think, how Euler method does it. So you solve for one time step, then you take all of those variables and you solve the next equations. So we use that solver. I don't have to write the solver. That is the best part of OpenFoam. I can just use the solver that is already written. Then we have to do initial boundary conditions, like we have to do for every kind of simulation. So we have different types of conditions possible. So I've already explained for patch. So for like an inlet type situation where you want it to have, or like for a membrane, or you want to do a like a film. You can use patch, which lets things in and out. Then you have wall, so where you want to restrict all kind of motions. You have symmetry, if you want to use a 2D axisymmetric or 3D axisymmetric type of domain, or you have cyclic if you want to just do a small part of your entire big domain. Then we can define different kinds of initial boundary condition depending upon what you want to actually calculate at the end. So like pressure, velocity, momentum, degrees of freedom, total internal energy, and that it's not limited to that. You don't have to define all of them. You have to just give the primary variables, and then it can calculate the rest. And also you can create your own initial values to give, and then it will calculate those values at other time steps for you too, if you have given all the equations. Then finally, the concluding part is to define when I will start my simulation, which solver I have to tell OpenFoam which solver to use, and what time steps I will be using, and then how and when to write the data. So I tell here to use SimpleFoam, to use a start time of 0 and end at 0.9, and then use a time step of 0.005. And then I tell it about what is the precision of writing, in which file format to write, and all that. But you can always get this already. You just have to change like which solver you are using, what is your start time, what is your end time, and delta t. So you don't have to write all these codes by yourself. They're all always present in the GitHub repository that I talked about. So if I look at my test folder, you can see like how the folders look like inside. And basically, just a minute. So if I already showed this, so you can see that we have a 0 folder, a constant folder, and a system folder. And then to run the simulation, I have to first do the meshing using block mesh. Then I segregate the mesh, like I made the zones, and then I refine the mesh. So my structure and the domain is ready. So this is a bit difficult to explain here, but OpenFoam is a command line based software on Windows at actually everywhere. So you have to use the command line. I was using getit to show you the graphical user interface, which can also be done on Windows, and then you can use that to see all your folders like we are used to. But then to run anything, you would have to use a command line. But I don't personally find it that difficult, because there are a ton of resources on the internet where you can find what these command lines are, and then there are like 3 or 4 of them which you have to remember, and that's it. Plus with OpenFoam, you already know what commands you have to write. I'll give you an example later. So I will just show here like how you can use the command line. So I use cd to go in to change my directory into the test, and then you can see the same folder structure. So I have 0, constant, system, and then I also have my inside my system, inside my directories also I can see what is what, and then I can also edit directly on this command line. So if I use nano, I can also go into my files and see what is written in them, and also edit them if I need. So these are probably the 3 commands that I use the most on the command line if I ever want to use it. And I'll also show you how I will use it to edit a particular file. So here I will edit the control tick file. So you can see here the SimpleFoam, start time, end time, but I don't want to run it for that much time. I want to reduce the end time. So I will change that to 0.9 seconds so that it can be finished quickly. So you can also edit directly inside on the command line. Okay, so this was my initial folder structure. So we have a 0, constant, system, and in system we have all the dictionary. So the BlockMech dictionary, the Toposet dictionary, Snappy Hexmex dictionary. So all the dictionaries that you want to write, it will be inside that. Also, you don't have to remember what dictionaries you need to put. There are always folder structures present for different test cases. You can just copy one and then make your edits there. In 0, so I have kept the start time as 0. If you want to, you can keep your start time as anything, and then you can start from there. But you have to keep the name of this folder also that. So it's here is where you keep all your initial boundary condition, and then the constant we will have our mesh. So once you run your block mesh, Toposet, and Snappy Hex mesh, you will have your polymesh here. And then you will have your different boundaries, neighbors, whatever you have defined in the boundaries will be recorded here. So this is your final meshing done. This is something that I do not use for the test case, but I think it's very essential to kind of show here that you can use OpenFoam to perform it on multiple processes. So it's to make your, first of all, task faster. So you can take your big job and divide it into multiple jobs, and then it communicates with each other, with each processor. But of course, it is limited by the number of processors you have. So how many processors you have and which method to use. By method, I mean this. So you decompose your domain into different sections, and then each section will do its own part of the equations. So it will solve the equation for each of these domain. Then at the end of time step, communicate with each other if there is something to be changed, and then do again. So what it does, it divide the task easily. It doesn't have to be just 4. I have shown here divided into 4 equal parts. It can be even higher. And then to run the simulation, we'll just play this. So to run the simulation, you just write the name of your solver and press enter, and then it solves. And you know that it is correctly solved when you can check these residuals, and you can see that the final residual is less than your residual, and you can also see your sum of your errors. Just pause here. So you can see like that your error has reached a sort of threshold, which is good. And you can also set these thresholds and perform the. So to show how I ran it again, so I just write simple form, which is the name of my solver, and then I press enter, and then it starts solving. That's it for running the simulation. And then if I go, like if it were a job that were being performed on different processes, I would also need to do this, which is to recompile the results back from these processes. So the opposite of the previous thing that I showed. So this was my initial folder structure, and then this will be my final folder structure. All my results compiled into their neat little tiny folders for each of the time steps that I wanted to see. And then this is the second favorite part for me in OpenFoam, which is Paraform, that you can visualize and use the calculator and the different Excel sheet sort of thing directly inside OpenFoam. So it can be used to do streamlines, deformation fields, particle tracer, statistics. I have personally used only statistics, so I'm not that helpful in the other part, but statistics, I can say that you can do very nicely from OpenFoam. So there are many different Paraform tutorials because it is a vast resource. There are many different things that you can do. You can directly graph from the tool. You can directly calculate your force, stress, strain, tensor. I have seen people calculate. You can also calculate all your secondary parameters that you want if you have your primary variables there. So many different resources, and it's always nice to go through these resources to see what other things you can do from what I show here. So you get something like this at the end. So if I run this, so I will just type Paraform, and then it will open up the user interface for Paraform. Right. Run. I'm so sorry. I don't know why these videos are not working. Okay, so work. Just a minute. Okay, so I can go to Paraform and I can see my domain. Then here I can select different mesh parts that I want to see. So I can select if I want to see just the porous cells, the support, and I can look into what is happening inside. So here I chose wireframe, so I can see like some parts which I have not chosen. My porous structure, yeah, there you go. So I chose the porous cells, and now you can see the whole structure. And then I converted it into surface, and you can see like how it is on the surface. So now I will choose the velocity field. So I chose here to U, and then this is my color map. I don't like the colors, so I will change it into a more rainbowish colors. And then you can use your arrows to like change your view. And here, if I play, I can see how my velocity field is developing. So like you see, my velocity is only now increasing on 4 of these faces, which face the inlet. So I will select the inlet, so you can see like that's the inlet, and you can see like the backside has not yet faced like the flow field. So there is 0 velocity there, but here at the big front, you can see high velocity areas. What's nice is you can also clip and slice your domain to go further deeper into your domains and see how that is working. So if I take my domain and I use clip, which is here in the 4th row, so that is the clip one, and then if I clip it, so then I like see just a portion, and then I can turn it around and I can see what is happening in this clip. I can also move where I want to clip it. It doesn't have to be perfectly in the middle. It can be anywhere, and you can move it around and see how the flow field is developing everywhere. There is also slice, which is like just one layer, which is sometimes what we do with CT scan. So it's kind of like a CT scan, but with computational modeling, and you can move your slice, and you can also see how your velocity changes in these slices. Here I've shown a prettier slice, so to prettier clip actually, to see like how the velocity is changing in this particular phase. So to summarize, in a work in an OpenFoam case is 50% pre-processing, so like making the mesh, how and where you want your refined mesh, and that is really very important. Without a good mesh, OpenFoam will not work. So mesh I will give highest priority to, and then 25% is running the simulation. If you have batch softwares and then sometimes the things don't match, so this is where you will debug a lot, because you will find out like what things didn't match. And then final 25% is post-processing, which is the visualization part. some helpful tips and tricks, because I'm also a beginner and I know OpenFoam can be very big if you consider, so this will make it easier. So first of all will be to use GitHub desktop to or just GitHub. You can also use the command line to always keep backup of your changes so that you know what changes you're making. I showed folder structure 100 times because it is that important. So whatever case you have, it needs to have your time directories, your constant folder and system, and these names are also important. And then where everything goes is kind of important to OpenFoam. So this always has to be kept in mind. Some of these you have to write yourself. Some of these OpenFoam will generate for you once you type in the commands. Only the run folder is mandatory, but I would suggest bringing in applications and the source folder also, so that you can make your own changes without hurting your source codes. Then use the forum and repository to find similar problems, and also you can find directly tutorials where they have these case files, and you can bring them in and you can change, let's say, the mesh to fit to your own situation, but you can use the rest of it as it is. Then you wouldn't have to change a lot except the mesh, and you can directly use whatever solver you're using. We didn't use it in this test case, but you can also use parallel processing on supercomputers, let's say, and then for very big domains, your task becomes easier. Here I've linked the Barcelona Supercomputing Center, which takes applications from groups if you want to run your simulations on their supercomputer. Then because I showed that they update their OpenFoam, so don't think that you need to update every time that they update, because the old OpenFoams also work pretty nicely, and they make like these tiny capital letter, small letter changes. So don't update OpenFoam while working on one of your projects. You can have multiple OpenFoam, but for one project, use one OpenFoam. The errors are well explained, but you have to read through the errors to find. Plus, these errors also have been faced by other users, and you will always find help in the forums. Naming your files, again, is very important, but that will automatically come because you have to be very precise in what you name your files, because OpenFoam only recognizes a certain name of a file and where the file is placed. One thing you can also do to check if your mesh is okay is use check mesh. It tells you finally mesh is okay, mesh is not okay, and this was the problem. So after your 50% of the work is done, you can use check mesh and then know that you're good to go to the next step. After I compiled this list, I found this nice PDF which also writes in a lot more tips and tricks than what I said, because they have probably used OpenFoam longer than me. So they found a lot more tips and tricks if you want to have a peruse. Then I found some examples of OpenFoam in mechanics where it has been used for biomedical simulation, for flow through coronary arteries, scaffold design. What I found interesting was it was also used for nozzle design in bioprinting. So I think it is being used a lot, but what I found was that only very simple solvers are being used: Icofoam, SimpleFoam, and PimpleFoam. Not a lot of different things that you would have to explore. So that's pretty nice. So you know that you will get support if you are using any of these solvers. Finally, I would like to acknowledge Redmond, which is my funding agency, and ESB for giving me this opportunity. Like I said, you can find the test case at this link. And then I would like to thank my group here for supporting me in silico tools for regenerative medicine. Thank you. And I'm open for questions, or if you want some kind of explanation for any slides.
Thank you very much, Sangita, for this very nice and interesting overview of OpenFoam. I can already see a couple of questions in the chat, so I can start with these ones. And in the meantime, you can continue typing your questions in the chat. So the first one is more a technical one. So can you please tell us where to download the software from again? I didn't install it yet.
It's called openfoam.org, and then you can see download on the top, and then you can download the latest version and whatever distribution you have, Windows, Mac, or Linux. Then it like writes it like from step one, like opening your system to how you will, what command you write where, and then it will install it for you.
Thank you. The second one is, for example, which kinds of non-Newtonian fluids are implemented in OpenFoam, just out of curiosity?
Which types of non-Newtonian fluids? Basically, it's not like you define a non-Newtonian, you can define any kind of viscosity and your I think it's called like viscosity dependent on material. I think you can define that and then it can solve it for those non-Newtonian fluids. There are also solvers available for non-Newtonian fluids itself. I think icofoam is one of them. So you can use that for your non-Newtonian fluid. And also pimple foam is also used for non-Newtonian fluids.
Thank you. So a lot of questions are coming now. The next one is, did you implement any custom functions in the code when using OpenFoam, or did you find that all the functionality you required was available from predefined functions?
That is a nice question. I always like that OpenFoam usually has what you need, but in some other folder. So let's say you are looking for how I will implement Darcy law, like how do I write pressure? How will it know that this variable is for pressure? So someone would have implemented the Darcy law or some variation of it. You just copy it and use the same way, and then you can find, like you can fine tune it to whatever you want. So I did use a special function because I didn't use the solver that was available. I used a DSMC foam, but we also appended a reaction part to it. So we had to write in the reaction, but we took a lot of inspiration from combination that has been done. Also old papers that did reaction, so they had some things written, and they used also the addition part from some other things. So yeah, it's always like you stand on the shoulder of giants before you.
Thank you. So the next question is, thank you for the interesting talk. Is it possible to couple a finite element model, so solid mechanics, with a CFD model in OpenFoam?
Finite element with finite volume. Yes, it has been done. So one of my colleagues in my old group, he used lights with OpenFoam. I also know that DEM, I think, is the software that is a finite element. So it has been done. I have not done it, but it is done, definitely.
Thank you. I can see a last question. Thanks for a very interesting overview. It would be great to have access to the slides, particularly with the resource links you have provided. So I think, yes, we can find a way to also make the links available. This session will be recorded and uploaded on YouTube, on the YouTube channel, as had already mentioned, but we can find a way also to make all the links available. So I don't see any further questions. We can wait another couple of minutes. If someone else has a question, just type in the chat. And maybe I can ask you something from my side. So sure. Would you suggest using OpenFoam also with very complex geometries for the machine part?
Yeah.
Okay.
Yeah, continue with your question. Sorry.
No, it was just like that. So if you, for example, have a geometry that you import from a CT scan or something like that.
I would especially say to use OpenFoam for that, because Snappy Hex Mesh is especially designed for these like complex corners and the tiny holes that you have, that like you can refine your mesh around these very complex parts and have a better resolution at these complex parts using Snappy Hex Mesh. So yes.
Thank you. There is one comment. Thanks to the speaker for a very interesting session.
Thank you. And apologize for all the videos. I don't know why they were not working.
No worries, it's normal. Okay, so if no one has a further question, I think we can close the session. So thank you very much, Sangita. It was really nice and interesting. And thank you
so much
to all the participants for joining us. And yeah, have a nice evening.
Thank you.
No, thanks a lot for the nice webinar. I hope everyone enjoyed it. So we will upload the video in the YouTube channel, so you can have a look again or inform your colleagues, friends about that. And we will be happy to answer your comments. Thanks a lot.
Thank you for letting me talk, and I also wish all of you a nice day and a nice rest of the week.
Thank you.
Thank you. Have a nice evening.
Bye.
Bye-bye.
Bye-bye.